This is mathheals.com, where you can find more links to math YouTube videos and computer science. Need to close some of these windows. Okay, this is a hypothesis test for a population mean using a classical approach by hand. The requirements for use this is samples obtained using simple random sampling or from a randomized experiment. Sample has no outliers, and the population from which the sample is drawn is normally distributed, or the sample size n is large. N is greater than or equal to 30. The sampled values are independent of each other. Now, specifically in this particular textbook we're using, they focus just on population mean where sigma is not known. Some books have both. They have where sigma is known and sigma is not known. So if you have one of those books, this is specific to sigma not known. Now, a classical approach by hand. First step, we write down a shortened version of the claim. Step 2, we come up with a null and alternate hypothesis, and H0 always has equals part on it. Step 3, see if the claim matches H0 or H1. Step 4, draw the picture and split alpha into the tails. If you have a not equal to on H1, that's two tails. If you have a less than on H1, that's a left tail. If you have a greater than, then it's a right tail. Now we'll find our critical values using the t-distribution table. We'll find test statistic. T0 is equal to x bar minus mu naught over s divided by square root of n. X bar is our sample mean, s is our sample standard deviation, n is a number in our sample, and the mu naught is a number off of our claim. And 7, if the test statistic falls in tail, reject H0. If the test statistic falls in the main body, accept H0. And determine the claim based on step 3. Excuse me. Note, practical significance refers to the idea that while a small difference between the statistic and parameter stated in the null hypothesis are statistically significant, the difference may not be large enough to cause concern or be considered important. It means you do a claim, and it says that there's maybe one's statistically significant difference. Maybe it's greater than, maybe it's less than. But when you look at the actual values from a practical standpoint, maybe that means one or two people or one or two individuals. So not that important from a reality standpoint. Let's look at our first problem here. Okay, the mean amount of fluid in a bottle of lens cleaner is 59. So mu is 59. It says mean and doesn't say anything about a sample, so that's why I knew it's mu. A researcher believes that the mean is actually lower than that. Sounds like our claim. So lower than 59. Um, 15 bottles are sampled. Sounds like our sample. So n is 15. And mean is found to be 58. So that's x bar. So x bar is 58. With a standard deviation of 1.2. So that's s. Now those are both sample values because it's referring to our sample, the 15. Test the claim based on this information that alpha equals 5%. So alpha is equal to 5%. Okay, step 1. Write down a shortened version of the claim. It did that. Come up with a null and alternate hypothesis. These are mu, since we're talking about population mean. Lower than, if that symbol, if I were to write it, would be less than, which goes here, and greater than or equal to, excuse me, goes there. Now the only symbols you can put on H1 are less than, greater than, and not equal to. Only symbols you can put on H0 are less than or equal to, greater than or equal to, or equal to. So when this was a less than, I knew it had to go on H1. Now these are opposites of each other, so if this is less than, then this would be greater than or equal to. Now a lot of books have adopted the convention of putting equals here. I don't really like that. I like the greater than or equal to because that means they're opposites of each other. Now, when they put an equals here, they'll always keep these, these three. You can have any of those three here, but this is always equals. So I want to point that out. I don't like it from the standpoint students seem to click better with these being exact opposites. If this is a less than and this is equals, they're not opposites anymore. Step 3. See if the claim matches H0 or H1. This is a less than, which less than symbol we put on H1, so it matches H1. Draw the picture, split alpha into the tails. Less than on H1. Less than on H1 means left tail. And we want to split alpha under our tails. Alpha is 5%. So put 5% there, and that means I put 95% here. Now for our critical value, it says use t-distribution table. Well, for the t-distribution, I need degree of freedom, which is n minus 1. N in this problem we said is 15. And 15 minus 1 gives us 14. And this is our t-distribution table. Now notice it says area in the right tail. That's wrong. It should say area in one tail. We don't even have a right tail here, do we? So area in one tail is 0.05. And degree of freedom is 14. So 0.05, this column, and 14, we get 1.761. Okay. Now, if it's on the left side, it's negative. If it's on the right side, it's positive. So you have to keep that in mind on the signs when using the t-distribution table. Now for our test statistic. Tells us to use T0 is equal to X bar minus mu naught over S divided by a square root of N. Well, X bar is 58 minus mu naught, which is 59, over S, which was 1.2, divided by a square root of N, so square root of 15. Key to plugging this in your calculator, put parentheses around top, parentheses around the bottom when you plug it in. Okay, so I'm going to have beginning parentheses, 58 minus 59, closing parentheses divided by beginning parentheses, and then 1.2 divided by square root, so second x squared, 15. And I don't need closing parentheses at the very end. And we get T0 is equal to negative 3.23. Now this is the number line. Here's negative 1.761. Negative 3.23 will fall over here somewhere. So for a conclusion, if test statistic falls in a tail, which it does, falls in the left tail, then you reject H0. Now H0 and H1 are opposites of each other, so if you reject H0, that means you accept H1. Now our claim matched H1, so whatever we say about a claim is whatever we say about H1 is what we say about our claim. We accepted H1, so we accept our claim. Now I'm working this kind of this way so I can see it all at once. I was working them side by side. This is my second attempt at this video. And see how the 1.2 here, for my second problem I put in 1.2 for the S also. So, and I didn't want to live with that mistake out there, so. Well, let's work our second problem. The mean amount of fluid in a bottle of lens cleaner is 59. So mu is 59. Research believes the mean is different. Sounds like our claim. So different than 59. 35 bottles are sampled, so N is 35. And the mean is found to be 63. So X bar is 63 with a standard deviation of 2.3. Since those are referring to the sample, that's why they're X bar and S. Test a claim based on this information and alpha is equal to 0.01. Okay. Back up to our steps. Write down a shortened version of the claim. We did that. Step 2, come up with a null and alternate hypothesis. Different than. That means not equal to. So I'll put not equal to on H1, which means this has to be equal. 59. Step 3, see if your claim matches H0 or H1. This is a not equal. We put the not equal on H1, so this one matches H1. Not equal to an H1 for a picture. Not equal to an H1 means two tails. So we'll have a critical value here. We'll have a critical value here. We want to split our alpha into the tails. We got 1%. You can take the 0.01 divided by 2 and you'd get 0.005. Now if 1%'s in the tails, that means 99%'s in the main body. Sometimes you need that, sometimes you don't. I just get in the habit of always putting it there just to cover. Okay, now we're going to use t-distribution for our critical values, which we know we need degree of freedom, which is 1 less than n, which would be 34. Okay, so area in one tail would be 0.005, which is this column, fourth from the right, and we want degree of freedom of 34. So fourth from the right, and 34 would be 2.728 if my eyes aren't getting off. 2.728. Let me double check that. That looks right. Now both of them are 2.728, but since this one's on the left side, this is negative. This one's on the right side, so it's positive. Our test statistic. We got T naught. This formula here is equal to X bar minus mu naught over S divided by square root of n. X bar was 63 minus mu naught, that's the number off of our claim, which is 59, over S, which is 2.3, divided by square root of n, which is square root of 35. Again, put parentheses around top, parentheses around the bottom when plugging into your calculator. So do beginning parentheses 63 minus 59. Closing parentheses divided by beginning parentheses 2.3 divided by square root second x squared 35. Enter. 10.29. Okay, this is the number line. Here's negative 2.728. Here's positive 2.728. 10.29 would fall over here. So it falls in the tail. So our conclusion, if test statistic falls in tail, reject H0. So we'll reject H0, which means we'll accept H1, or opposites of each other. Since our claim matches H1, that means we'll accept our claim. Whatever we say about H1 is what we say about our claim. And it's pretty obviously it's different, 63 from the 59, but it's significantly different. That's what the question was. Now the books will always use do not reject here instead of accept. I like accept and reject because students seem to click better with those. For some reason that do not reject kind of throws them. Let me save this. And yeah, that one's good. Okay. Let's look at our next problem. Problem number 3. The mean amount of fluid in a bottle bottle pop is 16.9. Research believes the mean is more than that. 10 bottles are sampled, resulting in following data. Test the claim, blah, blah, blah. Okay. Up here we need X bar and S. We're not given that. We're given raw data. So first, before we do anything, let's go ahead and find X bar and S. So let's see, I got my values here. I got 16, 16.1, 17, 17.5, 17.2, 17, 17.5, 16.3, 16.7, and 18.7. 16, 16.1, 17, 17.5, 17.2, 17, 17.5, 16. Okay. We're going to add those together. And I should have these numbers already in my calculator from the first attempt. So go double check that. Yeah, that looks good. Okay, and then so if I add those together, we get 170. Okay, so X bar, our sample mean, is going to be the sum of our X values divided by N. So we got 170 divided by, I think there was 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. So that gives us 17. Now we need another column. That's X minus X bar. So we got 16 minus, 16.1 minus, 17 minus, 17.5 minus, 17.2 minus, 17, 17.5, 16.3, 16.7, 18.7, and X bar 17. (16 minus 17 is negative 1. 16.1 minus 17 is negative 0.9. (17 minus 17 is 0. This gives us 0.5, 0.2, 0, 0.5, negative 0.7, negative 0.3, and 1.7. Well, then we need to square those values, which gives us negative 1 squared, or 1, negative 0.9 squared, or 0.81. I need to be double checking myself as I go along here. 0 squared, or 0, 0.5 squared, which is 0.25, 0.2 squared, which is 0.04, 0 squared, which is 0, 0.5 squared, which is 0.25, negative 0.7 squared, which is 0.49, negative 0.3 squared, which is 0.09, and 1.7 squared, which I think was 2.89. Let me double check those. I got them listed here in my calculator already. Okay, that looks right. Okay, now I want to add these together. Let's see, 5.82. So S is going to equal to square root the sum of X minus X bar squared over N minus 1, square root of 5.82 over 10 minus 1. 5.82 divided by 9 gives us .804155872. Now let me double check that. One 804155872. Okay, that looks good. Okay, now we're ready for our problem. Okay, let's see what they're saying. The mean amount of fluid in a bottle pop is 16.9. Well, that implication is it's mu. Researcher believes that the mean is more than that. Sounds like the claim. More than 16.9. Researcher, or 10 bottles are sampled. N is 10. And we found up above that X bar is 17. And S is equal to 0.8041558721. Excuse me. Test the claim based on this information that alpha is equal to 10%. Okay, these are means, so these are mu's. More than. The implication is that's a greater than, which goes here. That's greater than, this is less than or equal to. Our claim matches H1. Now greater than on H1. Greater than on H1 means a right tail. Now we split alpha into our tails. Alpha was 10%. So put the entire 10% here. This will be 90%. We need our degree of freedom, which if n is 10, then degree of freedom is 9. So area in one tail is 10%, and we're looking up degree of freedom of 9. So 10% right here, and 9, if I come down here, that gives us 1.383. It's on the right-hand side, so it's going to be positive. Now our test statistic. We'll have T naught is equal to X bar minus mu naught over S divided by the square root of N. That's off of our steps. Test statistic was X bar minus mu naught S over square root of N. Again, I'm just going through those steps. X bar we said was 17 minus mu naught, which is 16.9, divided by S, which was 0.8041558721, divided by square root of N, which is square root of 10. And no, you cannot round that. Typically, you don't round to the very end. You don't do it in the middle of a problem. So parentheses are on top, parentheses are on the bottom. Okay, so do beginning parentheses 17 minus 16.9, closing parentheses divided by beginning parentheses 0.804155 872 divided by square root of 10. So second x squared 10 enter. And we get 0.39. Okay, this is the number line. Here's 1.383. 0.39 would fall over here somewhere. So for a conclusion, our test statistic falls in the main body. If test statistic falls in the main body, you accept H naught. So you accept H naught, and that means we're going to reject H1 because they're opposites of each other. Now, since our claim matches H1, whatever we say about H1 is what we say about our claim. We rejected H1, so that means we'll reject our claim. And let me save that. Should be able to do that, assuming no other basic math error. Can't seem to get around making those.